Hey everyone, and welcome to this explainer. Today, we're diving straight into the fascinating and honestly sometimes frustrating world of industrial metallurgy. We're going to learn how to think like expert quality detectives, stepping right onto the factory floor to look at stamping defects exactly how a quality inspector sees them.
To really set the stakes for our investigation, think about this for a second. How does a tiny, microscopic scratch completely ruin a $100,000 luxury car? How can a flaw that's barely visible to the naked eye cause a massive failure in downstream assembly, or completely wreck a cosmetic finish? Well, when we're dealing with automotive Class A outer body panels or precision electronics, literally every single micron matters.
Let's meet our usual suspects. We'll be hunting down 4 main defect taxonomies on the floor today. We've got edge defects, like jagged burrs, surface defects, such as those nasty longitudinal gouges, forming instabilities that actually lead to penetrating cracks, and finally, debris contamination, which causes embedded indentations. Categorizing these flaws by how they physically show up is absolutely crucial. It's step 1 in targeted root cause analysis.
Okay, quick look at our agenda for this explainer. We're going from the inspector's mission, straight through investigating edge and surface defects, severe forming failures, uncovering debris, and wrapping up with the metrology toolkit. Let's get to it.
Section 1. The inspector's mission.
So why exactly is our role on the factory floor so vital? Well, it all comes down to the transformation process. Stamping forces flat metal stock into finished components through some incredibly complex stress states. We're talking everything from high localized tensile strain to severe compressive forces. Identifying defects early prevents huge functional, assembly, or aesthetic failures down the line. If we miss these anomalies, it can lead to anything from poor plating all the way up to total structural failure of the part. No pressure, right?
Let's move to Section 2, investigating edge defects.
So a burr, it is definitely not just a rough patch on the metal. It's a dangerous, sharp projection of stretched metal that actually extends beyond the cut edge profile. This usually happens when the fracture lines from the punch and die just don't converge cleanly, often because there's way too much clearance between the punch and die, or the tooling is just worn out. These ridges are a nightmare. They ruin flush assembly mating, they damage plating, and they introduce localized stress risers that completely wreck the part's fatigue performance.
Now contrast stretching that metal into a burr with what happens when the tool is forced to double break the metal. Slivers happen when the punch-to-die clearance is actually set too tight. The fracture lines bypass each other, creating this secondary shearing action that literally ribs off minute, razor-sharp ribbons, or microthreads, of metal. These little slivers are notorious for migrating around the die, scoring part surfaces, or worse, contaminating sensitive downstream modules.
Moving right along to Section 3, spotting surface imperfections.
Okay, let's talk about the visual culprits that ruin the optical uniformity of a part. As inspectors, we are constantly on the lookout for galling, which shows up as severe longitudinal gouges caused by micro-welding streaks between the sheet metal and the tool face. We're also hunting for Lüders lines, which look like flame-like strain bands, orange peel, which is exactly what it sounds like, a rough, pebble-like texture from coarse grain sizes, dents, which are localized pits, and surface staining from chemical discoloration.
I want to pause on Lüders lines for a second, because they aren't just scratches. They are a deeply complex, internal, dynamic strain aging phenomenon. They form these visible, wavy surface deformation bands right during the initial yield point elongation. On a microscopic level, interstitial carbon and nitrogen atoms suddenly unpin from dislocation cores within the metal lattice. This localized unpinning creates discrete bands of plastic deformation that get permanently etched into the part as visual ripples. It's a real headache to deal with.
Section 4. Detecting severe forming failures.
What actually pushes metal past its mechanical limit, causing it to neck, split open, and catastrophically fail? Well, the primary drivers include strain states that actually exceed the material's forming limit curve, an unfavorably oriented sheet direction relative to the coil rolling direction, insufficient punch fillet radii, and high friction from, you guessed it, inadequate lubrication. Any one of these can trigger a full-thickness fracture right along the strain plane.
It's fascinating to contrast a tensile failure, where metal stretches way too far, against a compressive failure, where it shrinks and buckles. With splitting, extreme tensile strain simply causes the metal to rip open. But with wrinkling, which is a compressive instability mostly seen in deep drawing operations, the outer flange circumference shrinks. That induces massive compressive stress, forcing those unsupported regions to buckle into severe wave-like folds.
Next up, Section 5, Uncovering Debris Contamination.
Let's become forensic experts for a minute and talk about slug pulling. This is when a piece of scrap, a slug, gets yanked backward and wrecks the incoming sheet metal. It's a four-step mechanism. First, a vacuum forms, trapping air under the punch. Second, oil film surface tension literally binds the scrap to the punch face. Third, residual magnetism pulls those ferrous slugs upward. And finally, excessive die clearance prevents a tight press fit of the slug in the die button. When that slug inevitably falls back onto the die face, the next press stroke smashes it directly into our fresh workpiece. Boom, massive dent.
Finally, Section 6, the Metrology Toolkit.
Standard visual checks under ambient lighting? Yeah, they just aren't going to cut it for finding the invisible flaws we've been talking about. That's where highlight oiling comes in. Think of it as an optical amplifier. First, you wipe the stamp panel totally clean. Then apply a uniform coat of high reflectivity oil and place it vertically under a high-intensity inspection light bar. That highly reflective oil film distorts and refracts the light around minor surface lows and pockmarks, making sub-micron depressions instantly visible to a trained eye. It's like magic.
Another incredible technique is whetstone polishing. For this, inspectors grab a fine-grained aluminum oxide stone block and rub it in long, continuous longitudinal strokes across the panel. Because the rigid stone only hits the high points of the sheet metal, those areas are abraded to a bright metallic finish. The low areas, the dents and surface defects, stay untouched and dark. You are literally physically mapping out surface depressions by hand.
Now this brings us to a really interesting crossroads: manual tactile inspection versus automated inline metrology. Manual inspection uses incredibly sensitive, specialized thin gloves. A trained artisan can sweep their palm across a panel and literally feel surface elevation changes and burrs as tiny as a few microns. It's an art form. On the flip side, automated inline metrology uses AI-driven, high-resolution CCD cameras to inspect 100% of stamped parts in real time right on the press line. The speed and accuracy are just mind-blowing.
As we wrap up this explainer, I want to share a quote that perfectly sums up our ultimate engineering goal here. Quality assurance in sheet metal stamping requires transitioning from reactive post-stamping inspection to proactive, in-process defect prevention. We don't just want to catch defects after the fact. We want to use our detective skills, our finite element simulations, and smarter tooling design to stop them from ever happening in the first place.
So I'll leave you with this final thought to chew on. As AI vision continues to evolve and those automated inline systems get faster and smarter, will they ever truly replace the artisan touch, the tactile sensitivity, and the raw intuition of a human quality inspector? Think about the future of manufacturing and where your own detective skills will be needed next. Thanks for hanging out and exploring the crucial world of quality detection with me today.